Hi everybody, it's Saltash Maths Tutor, and today we're going to be doing graphs of trig functions, and this will support the Core 2 AS level maths. And as me old mate Brian Blessed would say, because he's always round here, he's stealing my hobnobs, he'd say, "What's wrong with trig functions? Big trig functions." And the simple short answer is, you all hate them. Because they're just difficult to sometimes get your head round on what you've got to do. So this is what this video is going to do. Just go through sine, cosine and tan and sort it out. So we will start with sine x. Sometimes you might see it written as sine theta. Don't stress too much about the whole theta or x thing. It is about the sine graph. Okay, so we're going to start building up sine x, which you will see, and I'm going to write it like that. It could be sine theta, but it's that. You may also, everybody, see it written as y equals sine x, and we'll sort of come to that in a minute. But the one thing that I do want to just reiterate is exactly what sine is. Remember that the sine of anything, remember the so, car, toa bit? Well, some people write so like that. I tend to write it like that. It's only because then I know the sine of any angle I want, theta, x, a, doesn't matter what you call it. We'll call it theta, just a bit of change in notation, equals. So if you like, I've done, let me just find a good colour, everybody. I've done the sine bit there, equals the opposite. So I've done that bit there, and see the way I've written it? The way I've written it, I've put the O over the H, so the O over the H. It's just a reminder. It's just the way my feeble brain, everybody, works through these things. So next we have to think about some scaling. This is just a grid, so this is the x-axis and this is the y-axis. That's all pretty cool so far, and now we need to do some scaling. Oh no, not the scaling bit. This is the nightmare, isn't it, everyone? Okay, here we go. We take a deep breath and we start working. Now we're going to work at these intervals. And these and you'll have to excuse my drawing, but these intervals are at 90 degrees, they are at 180 degrees, 270 degrees, and 360 degrees. And for all of you mathletes out there, we could also write this in radians. Radians, which is pi over 2 radians, pi radians, 3 pi over 2 radians, and 2 pi radians, yeah. And I'm just going to move that radian notation just slightly down so it doesn't confuse the graph too much. And I sort of forgot, but we need to label this as 0 here. Okay, now we get to draw the actual graph itself, and for sine, we're now going to blimey, we're now going to create these sine waves. So it's using this bit here. It's what value of y, where am I going to mark on here when I put a value of x in, and that's the value of c that's running along here. So to get the graph going, we can start putting some values in, and unfortunately these are things that you're just going to have to basically get to grips. Learn one or two in each of the trig functions and you're away. So the first thing is, I know that the sine of 0 is 0, so the graph's got to follow or go through there. I now know that the sine of 90 is 1, so I can put a mark up here. I know that the sine of 180 is also 0, And because I know that it's going to be something along the lines of, it's going to be something like that, isn't it? We know it's going to be that. I can start to, you'll notice I did it with the 0 there. I can put my 180 on there. And I can now start to draw the graph. I also know that it is repeating itself. The word periodic, which means it repeats itself, and I know that for the sine graph it repeats itself over 360, and I sort of know, don't I, that there's got to be, it sort of goes like that. So I have to look for that symmetry in the graph. So I know that 270 is -1, and I'll just repeat, I'm sketching here, and I know that 360 is 0. And what I've ended up with is the graph of the sine wave y equals sine x. When I've just put these figures, or even I could put the radian figure in there, and come up with these numbers. Now here's an important thing. So from our calculations we know that the maximum value I had, the maximum value was here when the x value was 90 or pi 2 radians, pi over 2 radians, and the minimum value is here. So there is a minimum and a max. Shall I write that? I will. There's a max value and there is a min value. What else do we need? Well, another thing I need to know about the curve is anywhere along the line, if I take the vertical distance from the x-axis up to the y value, any of these, then that is the amplitude of the sine wave at that moment. And just to stress that the trig function, the sine theta sine x thing, is periodic and repeats itself over 360 degrees or 2 pi radians. What that means then is, and what I've done is I've just copied the yellow part of the graph. I'm just going to dump it here, which means that that fits nicely onto there. And my graph is sort of pretty rubbish, but these intervals here, let's just pick up the colour, these are 90 degree or pi over 2 radian intervals, and so that you can see that I say that, don't I? You can see, well, I'm hoping you can see that this curve here, which is one cycle, is then repeated, use different colour, here as well. Okay, so just a few final points, the proper nerdy stuff. I've just minimised up the graph there and shoved it in the top left hand corner, and if you like I've just highlighted and expanded this bit, and that's now down here, because what I want to do is just talk about some of the symmetry aspects and some of the other phraseology that will come up. But there's if you like, one basic concept here is about, sometimes you'll see, sine 30 equals, well, it's a half. What does sine 150 equal? And you're meant to go, it's a half too. And why? Well, the graph sort of tells us why that should be. Because sine 30 is going to be, well, 30 degrees, and this is my x scale here with those on, and there's 30 there, roughly, obviously. So if I then go up to here, at that point there, the value I get, and I stress again, the diagram is rubbish on my part, but please try and imagine that that's where y equals a half. That's how I'm working out that calculation, that this is my sine theta, or x, whatever you want to call it, which is in fact sine 30, and I can actually read straight off the graph and go bump, what's the y value, and here it is, a half. But that's not the only time that y equals a half, my dear friends, because if I were to, I'm trying to get a line here, it's not working, here we go, there we go, with that line. If I take any horizontal line which is passing through the y equals a half value, you see what that goes straight across the line. You'll see it also cuts the axis in a different place. So let me just draw that. Oh, that's rubbish, isn't it? That is really quite shocking. There we go, that's a bit better. And it cuts there too. And so there is a value here. And what is that value? Well, the value is, and what's a good way of describing it? Well, if you like, you can almost see, because the line is perfectly symmetrical, then whatever that value there was, and we know that it was 30, because it goes across my perfectly formed, and you can tell by the artwork it's good, everybody, perfectly formed sine wave there, that whatever that space here must be the same space there, the same distance or value there as well. And that's absolutely right. So without having to think too much about it, or maybe having a little think about it, I can say this, that the sine of 30, which is what we have just worked out here, is the same as the sine of 180 minus that bit there. And I know because of the symmetry it must be the same, so it's 30. In other words, it's the same as sine of 150. And that, my friends, is when they talk about symmetry, that's what they mean. They mean, where does this y value, where does this horizontal line cut the wave also? And in this case we put the sine wave up, and so these values stand. And here's the sort of final thing I've got on the sine wave thing. And this, everybody, completely fried my noodle when I first saw it. What the hell does that mean? Well, it was this relationship, which was the sine of minus x equals minus sine x. Are you having a laugh or a giraffe? What the hell does that mean? Well, when we come down to using the graph, it hopefully becomes just a little bit easier. And here's probably by example is the best way of doing it. And that is, if I have the sine of minus 30, well, let's plot that on straight away. And we will pick, no, we're not going to pick green. I was going to pick green, but I'm going to pick yellow now. So we're going to have minus 30. And we know that what we do to find the y value is we trog on down here. We don't do that, we trog on down here. We take that value there and we go across and we read off the y value, But we know, because this lovely curve is so perfectly symmetrical, we don't have to think too much about it, that there must be some sort of symmetry, because if I've got 30 here, take the value up and across, I know it's a half. And because this curve is a perfect sinusoidal wave, everybody, then that must mean that if I go down here and across, that value must be minus a half. And then suddenly I realise this, that if I've got sine of minus 30 equals minus 1/2, then, because I've just used it, I've used this bit here, haven't I? I can say, well, sine of 30 equals a half. This must mean that minus sine 30, i.e. flipping it here to the value there, that must equal minus a half, because there's this perfect symmetry thing going on. Another example then would be, well, what is sine of minus 90 degrees? Well, okay, I'm going to go to my graph. There is minus 90. Go down to the graph, then come across, and the value is, poorly drawn everybody, of course, is minus 1. I can now ask myself, well, what's the sine of 90, well again I'll go across here to this point, go up on my graph, and it is 1. Well, how do I turn this into, sorry, wrong way around, how do I turn that into this? Well, I have to minus it, I have to minus the whole thing. So minus sine of 90, just like minus sine x up here, equals minus 1, which is the same as, everybody, that answer there. You also might see this written as the function of minus x equals minus f of x. Guess what, everybody? It's exactly the same. Exactly the same. And the other thing that you've got is that sometimes the sine trig function is also referred to as an odd function. And the way I remember that, when I'm struggling, is that, if you like, it's almost a flipping of the function bit. I have a function here, and that equals a minus function. Even to me would be plus and plus, or minus and minus. This isn't mathematics, it's just me doing my brain thing here. So the fact that I've got, if you like, a positive function and a negative function makes it odd for me. Now, because we've got some of the terminology and ideas with sine function, it's actually the cos x, cos theta function becomes a little easier. Same ideas, just slightly differently drawn. Now what you'll see is that I've drawn actually what is the sine graph onto this grid. You see I've labelled it up with exactly the same numbers here, same sort of x scaling, it's not sort of, it is the same x scaling. And the thing about the cos trig function is, if you get the sine thing weighed off and sorted out, all that you do with the cos function is it shifts to the left, like that. So you get that sort of effect. Now that's not a hugely, I understand that, not a hugely mathematical explanation, but that's sort of what it's about. It just makes that one shift, and I'm just adding a few bits on here to so see the cycle slightly more clearly. It is a shift, if you like, 90 degrees. We shifted it 90 degrees to the left. So I think in a learning way, get the sine rule weighed off, just notice a little shift left and you move it over. So I'm almost suggesting learn to plot one and the other one rolls out. The minimum and maximum values, that's obviously the maximum, everybody, and that is the minimum values remain at 1 and minus 1. The amplitudes are exactly the same, that's all exactly the same as the sine, or the concept is the same. As I did with the sine thing, just a reminder, it was so car, and again I write that as, I write it down here, cos, that's this bit here, of theta, or it could be x, or it could be the angle you want, doesn't really matter, we'll just call it theta equals, and you may recall I wrote so slightly differently, I write car like that because it reminds me that it is the adjacent over the hypotenuse. Also, to restate that cos x is periodic, it repeats itself over 360 degrees, so just to sort of stress that, here is the 360 cycle. That's not the 360 cycle, everybody. Here is the 360 degree cycle taking place. What else have we got? Well, we've also got that idea of, as you know in the sine, we knew a value, where else did it occur? So let's just look at cos of 60. So if we look at, as my example, cos of 60, well that equals a half. So cos, there's 60 on my x-axis. I then go up to where it hits the waveform, come back, and on the y-axis that's where it says half. But as we did in the last section, where else does it occur? Well, it also occurs here too. And what is that value? Well, it's again that whole symmetry thing going on. If you like, it's an idea of how much distance is here. Now, because this is, I'm just drawing it on again, this spacing here is 60, I know that and I'm just trying to find the right colour. If you like, from here to here is 60 from the peak. Well, here's the peak here at 360, again badly drawn, I know. So that's 60 back from there, which means that cos of 60 equals half. Well, also the cos of 360 minus 60, which equals the cos of 300, equals a half as well. Now we also talked in the sine function about it being odd. Well, cos is an even function, and very quickly I'm going to sketch this out. I've got my graph here. I'll do this bit here, so that's 90 and that's minus 90, so effectively I'm copying this bit here. And you can see that if I went for, again we'll use 60, the value for 60, go up to the graph, and that is a half on the y-axis. Well, if I take the line over horizontally, it's a half here, and if I go down, then that's when it's minus 60. So in other words, it is an even function because, and let me use that functional notation that I used before, then f of minus x equals f of x, or the sine, the cos of minus x, i.e. minus 60 here, equals the same as cos of x, the 60 here, because we know they both equal half. Okay, and finally we're going to get to tan theta. Remember, that can be written as tan x, but it's the tan trig function is the main bit of this. And this, everyone, is the different one. And whereas cos and x have maximum minimum limits, remember they had the maximum and the minutes here, which were 1 and minus 1, the minimum and maximum values, that's what I meant to say. Well, great, tan doesn't. Just again a reminder, for tan, TOA, again I write it as TOA like that, which is the tan of any angle you're after equals the opposite over the adjacent. Let's just get rid of all of that. So that's just a smally reminder of that. So here comes the crazy tan curve, and the first thing is that it looks like this basically. Comes out of the 0 point and curves up, and it never quite touches the 90-degree point. If I went the other way into the negative, it would go down here, and there would be another, it's our new word for the day everybody, asymptote, and that's not meant to be touching, but that's just my drawing. Now these asymptote, I suppose I better write the word asymptote. Help everybody. Asymptote. I don't think that's right, hang on. Yeah, it's because of banana. Why am I saying asymptote? I don't know. Asymptote. It's an asymptote. And the asymptote, the yellow thing here, basically means that it is undefined at 90, plus or minus 90, and in fact if we were to draw the graph on, then we would find that it looks like that, and it basically repeats itself backwards and forwards along the x-axis, but at each one it is undefined. And let me just say why that is. Well, I've just roughly drawn out a triangle of tan, so tan theta is the opposite over the adjacent. Okay, let's not do that at all. Let's just shift this down to here. Let's start to increase the angle. So if I increase the angle, and that's my new theta now, you see that the opposite is getting bigger and the adjacent is getting smaller. Well, let's take that on one more. Now the opposite's got even larger and the adjacent got even smaller. In fact, what we could say is the adjacent is, and we'll use a bit of mathematical notation, is tending towards 0. And in fact, let's just say it gets to 0 and the opposite tends towards infinity, becomes massively large. Well, we know that anything 4 divided by a negative number becomes undefined. It doesn't exist. Let's be precise here. It is undefined. So the values that are here, because of this tendency for the adjacent to get smaller and 0, and the opposites get massively large, means that there is no value. It is undefined. Exciting stuff, eh? So just back to the graph now, and whereas the sine and cosine are periodic over 360, I'm hoping that you can sort of see that the tan, its period, is just 180 degrees. That's all it is. As far as the symmetry goes, well, it's sort of, I find it a little bit easier, really, to be quite honest. Because if we, and I'll take an example of this, if I have tan of 45, well, let's mark 45 on the graph here. Go up till I get to the curve and come across the y-axis, that being obviously the y-axis, then the value is 1. I can see, though, that if I then take my horizontal line, where else does it cut? Well, it cuts here as well, which is, whatever that distance is there, is that distance there. What that means then is tan of 45 equals the tan of 180 plus 45, which would equal the tan of 225. So see how I did that mental maths then? Oh, crikey, Jedi! And same as we've done with cosine and sine. Is it odd or even? Well, what do you reckon? Well, it is odd. It's not odd the question, it is odd, because again, if we take, let's pick another colour, blue, should we have blue? Tan of 45 over here we know is the value of 1. If I go to minus 45, come down, that value must be minus 1. So in other words, what we're saying then is the tan of x, in fact let's not say that, say it in a different way, the tan of minus x equals minus tan x. In other words, the tan of minus 45, which we know equals minus 1, equals minus tan of x, and we know that tan of x equals 1 equals minus 1. Makes sense? The graph explains it better than me, I think, in this particular case. So everybody, that's been Saltash Math Tutor. Half an hour of excitement, eh? Graphs of trig functions. Got any questions, then post them up. Put a comment on. I'm happy to go into any of the bits for you again, but that is a revision for your Core 2 graphs of trig functions. Thanks.